So when dealing with a rational function, which we could call r of x, and we'd have n of x over d of x, which basically means a rational function is we're going to have a function in the numerator and a different function in the denominator. We can look at those functions as a to the x to the m plus dot, 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 over b to the x to the n plus dot, 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 dot. It really doesn't matter, but remember in Algebra 2 and even Algebra 1 we talked about, or Algebra 2 at least, we talked about taking a polynomial and rewriting it in standard form, meaning that you're going to have your largest degree first and then going down in descending order, right? And then you identify the leading coefficient and the degree. So assuming that I have my two functions, we want to make sure that they're in standard form, where a and b represent the leading coefficient and m and n represent the degree. So when you guys look at this polynomial, you'll see that both of these are written in standard form, right? Where the degrees are both 1, and my leading coefficients are 1 and 7. Does everybody follow me with that? Okay, so as long as my rational function is in that form, there's some tests for horizontal asymptotes. The horizontal asymptotes, if m is less than n, then y equals 0 is your horizontal asymptote. If m is greater than n, there is no horizontal asymptote. And if m is equal to n, then y equals a over b is your horizontal asymptote. That's the horizontal asymptote test. So we look at this. We know that m and n represent our degrees. Our two degrees are 1 and 1. Well, those degrees are exactly the same. So the horizontal asymptote is going to be the quotient of your leading coefficients, which are a and b. Well, a represents the leading coefficient of the numerator. B represents the leading coefficient of the denominator. So therefore, you can see that my horizontal asymptote in this case is y equals 7 over 1, which is y equals 7 is my horizontal asymptote.